Okay, hello. Welcome back to one of my video log recording sessions where I talk about genetic algorithms. Date is 2025, April 18th. And today, or rather tonight in this session, I'm going to be, well, this session isn't that special, but it's kind of maybe special because I'll be reviewing the concepts or what I've been doing for the past 2 or 3 weeks, maybe even a month as well, and applying that to one of the old Jupyter notebooks that I did last time, and also making some structural changes in how the notebooks are arranged in terms of code and importing and stuff like that. Yeah, so this session might just feel, somewhat all over the place. But anyway, here we go. So today I felt like, let me just rephrase that. I decided that it is a good idea to revisit this particular notebook, genetic algorithm grid search 350 items. Now, as a reminder, this notebook was where I had 50 preset items and therefore 50 preset utility values and 50 preset constraint values. And previously, what this led me to do, or rather where this led me, was this. Let me just copy this and paste it to Paint. So when I did this is for the top 10. This is the utility. This is a sum utility value plot for the top 10% entities, average of top 10% entities. And these peaks, 1, 2, 3, 4, maybe 5. I'm sure I did like 1, 2, 3. I did 10 iterations of the evolution, so there are supposed to be term graphs. But anyway, the important thing is there were peaks, and there were the plateaus. So naturally there will be the average peak and the average plateau, and where there's a peak and a plateau, there's always a dip, naturally, because this difference is the dip. And relative to the peak, how big is the dip, which I called the dip size, or because I just used the word relative, dip percentage or dip size percentage. And this led me to, not naturally, but I couldn't just focus on this, as in I should have, but I didn't or couldn't, and therefore I wanted to explore the relationship that dips had to different distributions. And then when this happened, it naturally led me to adjusting and readjusting the max constraint, which is calculated, or which can be calculated by setting the max constraint percentage which led me to create peak plateau plots. Something like this, or something like that, or something like this. You remember these peak plateau plots. Honestly, I don't know if other people actually call that. I just named it like that, so it's not official, but I just call it like that. So, but today what I did is kind of retrace, because once I started looking into different distributions, all the items and utility values and constraint values had to be, sampled or generated from these distribution plots, either from one distribution plot or from two different distribution plots separately, always separately, but still either from one same thing or from two different distributions. But today, as I retrace this, there won't be a peak plateau plot, because I would already have the 50 items preset, which naturally, eventually, or automatically rather, that's the right word, automatically gives me the max constraint, or not really, the total constraint it gives me. And since in this previous old notebook, Jupyter notebook, I had the max constraint all set here, right? Hold on. There we go. Max constraint there, and hyperparameters. See, it's all gone there but anyway, in this notebook I have the max constraint already determined here. It's 9,000. So, for example, 9,000 is the max constraint. So because I have that, I don't need this. This will be calculated by dividing this by total constraint. And I won't have the peak plateau plot, because the x-axis of the peak plateau plot is the max constraint percentage. So I won't have that. And I won't have the distributions, because I already have the preset items. I won't need to consider this first. So all I need to do, or rather all I ended up doing, was use these settings to apply all the slightly more advanced ideas, such as the new compute plateau plot and the new and also compute the average peaks, and just compare. And while doing that, also use the new evolution scheme. Okay, along with the new slightly modified selector and things like that. So first, let's see what I actually did when I did this. When I did the genetic algorithm grid search 350 items. And spoiler alert, or TLDR, I am really ashamed that I did it this way without actually thinking about it. So I'm not proud of this, but good thing is now I know. Bad thing is I've been doing it somewhat the wrong way, or not in the entirely correct way. Sorry for sniffing. Okay, so what did we do? For example, if I were to have 10 iterations of the evolution, I would, as soon as I have the void genes, and then I would introduce the genesis into the world in the list of lists or list of entities. As soon as the first generation starts, I would use the selector, which I don't right now, which I don't do in the new evolution scheme, because I don't need to, because I'm always starting with the new genesis, which is full of void entities, void genes. So there is actually nothing for the selector to do. Everything just weighs 0. So I don't need that. And I would do that at the end anyway, at the end of each generation. So I don't need this right now. But previously I did it, so that's one thing. And then I would rank the entities by creating entities dictionary, and then ranking them by the keys, and then recreating the world by making it into a flat list, and then calculate the current population and compute the average of some utilities for the head, for the tail, and for the top 10% and for the top 50%. For the top 50%, I don't do this anymore because I don't think I actually need it. I might actually need it one day, but for now I don't do this anymore. So it's only the top 10%. And then I calculate the num create, which is how many more entities do I need to create to refill the population or repopulate the world. And then if the num create is below 0, I set the num create to 10 anyway. And then if it's not, I just pass. And then I use the favoring highest procreate function. And then here, every time the procreate function is used, I would have 2 children, and I would add those 2 children to the world. This part, I would have the world. And then I'd add the new children at the very end. And then I would limit the population somewhere there. If this was the if this was pop size, I would limit the population to 1.4 times the population size, and then I would let every entity mutate, and then that would be the end of generation, and end of one generation. Yeah, so that's how it used to be, but in some cases it could have been that the 1.4 times pop size mark could have been somewhere here, and therefore too few new entities, which are from the entities with somewhat higher scores, relatively high scores, so they're offsprings of these. So too few of these would end up in the new world for the next generation. Sometimes you get cut off here because so many got deleted here, but that's usually not the case, because entities with low scores would in most cases have a very low summed constraint value, and the selector wouldn't strike them out, so they would just be sitting there quite peacefully. So I wasn't getting that many new entities in the world. So that's what I used to do, and that's what led me to this, the dips. And then so next up, I wanted to, as I was recreating this notebook, into another notebook called Genetic Algorithm version 2. And well, I'll go over this first. These are the values, 50 values, and these are the constraint values, the 50 constraint values. And if I were to get a histogram, this is what it would look like for the utility values. And for the constraint values, this is what it would look like. So they're kind of log normal, they're right skewed. So I go to the general genetic algorithm grid search for log normal, the final version, where I still had the older evolution scheme, and I have a look at the closest peak plateau plot, which is for 40 items, because here I have 50 items, so 40 items I go there, and then I look at the peak plateau plot over there, and then I'm reminded that I don't know what the max constraint percentage here is. So as I had a look at the distribution of these values, how the distributions look like, and as I set the hyperparameter, which is where max constraint is set to 9,000, and the summed constraint values is 10,850. So I do the math. I divide the max constraint by the total sum of constraint values, and it gives me 82.94%. So I go back to the peak plateau plot and I look at somewhere around 80. That's what it usually looked like. And at around 80, average dip percentage was between 12 and 14%, which sounds about right, because from anywhere from 10 to 15% when it comes to dip percentage is what I have been getting quite consistently, and that's about right. So this is how it used to be in the old one, low normal, and this is how it will be, or how it is, with the new evolution scheme. So I go to the 40 items, the closest one to 50 items, and then I have a look at the percentage plot around 80, which is about 3% ish. Peak plateau plot, yeah, doesn't matter. And I look at the summed utility plots for the across the generations, where max constraint percentage is at around 80%, and I see no peaks, or well, I don't see much of a dip, and the average dip percentage here is 2.8%, so less than 3%. So theoretically that's how it should be. Let's see if that actually was the case. Now this is the new, coming back to this, but this is the new notebook, as you can see, created on this date. Some structural changes. I decided that in order to well, for me to run things possibly on AWS EC2 instances, I had to, or rather it was better for me to start having separate Python files and have the codes or the scripts that will be shared across other files. For example, all these functions. for now I only have functions. So organize all these functions into different, either one huge Python file or just 4 separate different Python files. Yeah, so that's what I did. So now all I do here is at the very start I import the necessary functions, and then now here I have the 50 items copied from the old notebook. I didn't want to have a JSON file for this, or you know, I didn't want to have this as a data file. Yeah, anyway, I have the 50 items here. I have the utility values, 50 utility values here, and the distribution, kind of log normal. I have the constraint values, 50 constraint values over here, and the distribution is kind of log normal, you could say, or exponential, depending on how you want to, you know, look at it. And I set the hyperparameters. Max constraint is 9,000 in this case. Population size is 1,000, and number of items is 50. You know, as I've already said. And yeah, so this does not get used anywhere, but I just wanted to know what the max constraint percentage is, and it is at, as I've said 10 minutes ago, it is at 82.94%. So we can just say that it's somewhere there, somewhere here, or in this case it's somewhere here, and it's a correct prediction. And then I go through these parts, you know, not really necessary, but I wanted to keep them for, you know, for the sake of robustness. And yeah, I go through this, and then here, the new evolution scheme has been applied here. So I start with the empty entities dictionary, I rank the entities, and then recreate the world in that order, you know, from entities with highest, or rather high sum utility values, and utilities with low entities with low utility values at the end of the list. And here's the I get the current population. I had to rewrite some code, or rewrite some code, because now that the code is different, some variables had to be, you know, input, you know, treated as new input into the functions that are being imported. But anyway, that happened. So I ranked it. I store the metrics. I set the numCreate value to 3% of the population size when numCreate is below or equals 0. And let's not forget, I also included the equal sign to the selector function. Yep, that's what I did. So that when an entity hits the max constraint, it doesn't get struck out. It remains there, because that was actually the very definition of a max constraint. You cannot go over it, but you can just stay at it. So that's the logic behind it. I set the new entities percentage to 0.5 or 50%. I select the new entities, allowing for duplicates, and then I add the new list of newborn entities to the front of the world, and then I let them mutate, and then I apply the selector function, and then I limit the population back to its maximum population size, which is now, you know, which is now 1.0 times population size. so the population size itself. But sometimes I would have it to 1.4 or 1.0, but for now let's just keep it at 1.0 for the sake of speed. I've covered that part in my previous video. So this is the new evolution scheme, and what you get here is this is the distribution of the entities towards at the very end, and the maximum ever was 1540, as opposed to well, not opposed, but compared to 1480 in the old notebook. So quite a bit of an improvement there. And then when I look at the sum utility plots for the heads, they constantly keep on hitting the maximum ever, as opposed to this one. It does that only once and then it never gets there, whereas here it just stays there. For the tails, well, the only thing to look at here is that the tails have also plateaued at around 600, slightly above 600, whereas in the old notebook they were all below 400, or sometimes above 400, but mostly below 400. So about a difference of 200 sum utility values. And sum utility plots for the top 10%, the average of top 10%, we now don't have a dip. But we'll look more into that. Top 50%, we don't have a dip. Whereas we used to have dips, even for the top 50%. And if we zoom in until generation 80, this is what happened. It just rockets up and plateaus up there, but slightly below 1400, whereas that wasn't the case here. Yeah. Again, it is sad for me to mention that this difference, or these differences, were at the cost of striking out entities with low utility, sum utility values, because I still think that there is some value, some merit to keeping entities at the lower end. And it might sound silly to say, but it is all for the sake of diversity, because you never know what the problem space will be in the future. So it is kind of my goal to keep this sacrifice to its minimum. But anyway, this is until generation 150. It skyrockets and then it plateaus. Generation 200, cool. Now, it says new assessment here because this is where I started applying the new or slightly more advanced concepts. So I get the average peak list, or in order to get the average peak, and the average peak was 1412.429999 something. And when I plot that, that's this red line, red dash dotted line. So there are, and obviously, of course, still peaks. And then I create the average plateau list in order to get the average plateau. It's called a list because previously this was used for all the maximum constraint percentages. So there would be 20 values, but now there's only one. So there's only one. There's only one max constraint, and therefore there's only one average plateau, which is this. 1362. And when I plot that, it's here, this blue line. So there are still dips, but these technically there is still something of a difference between the peak and the plateaus, and by definition, you know, it's natural, but the behavior or the characteristics here is different. Because when I said, or when I call something like this a dip, I call it a dip and I call this a plateau. Well, I call this a peak. Let me just do that. Compare this. Now, when I should I do it in red or white? What's a good color? Black. Okay. When I call this a peak, and when I call this the plateau, and the difference, the dip, it was implied that they never recovered. But here, these, well, this is the average peak, and this is the average plateau. And the difference here between this one and this one is that I don't even have to zoom in, but they do recover. When they fall down, they do recover. Eventually. Even for this purple line. It was the peak at its peak here, but naturally they fell down. The entities fell down. But they do recover somewhere. Let's look at another line. This green one. It was there. It was at a peak here, and they went down below the plateau. They stay there for a bit. The green line just stays there for a bit, but it did come back up. And towards the end, it did go back down again. But I'm sure that if it were given more generations, for now it was the maximum generation was 500. That was the end of the line. But if it was set to 1,500 or just 1,000 or 3,500, I'm sure that this will go back up and just stay within this line, within the plateau and the peak, within this range. So that's what happened. And then I zoom in and I look at only one of the iterations, and then it just stays there. However, if you look, this is until generation 150. Oh yeah, before I go there, it would make sense for me to mention this too. And because now that the entities with lower summed utility values are being, struck out, left out, and newborns are being added, which have more potential to, more success. I don't want to call it success. Which newborn, and now that more newborn entities from entities with higher summed utility values are being introduced to the world and passed on to the next generation, because they have more potential of having higher summed utility values, the plateau level is higher. It was somewhere slightly above 1,000. What? Give me red. It was slightly above 1,000. But now it's, as we've seen, what was it? 1362. this is 1362. So there's a difference about 300. %30 more. So I got rid of the dips that were something like 12 to 15% difference. You know, when you compare the dips, the peaks and the plateaus. At the same time, the plateau level just rose up by 30% by doing that. Again, at the cost of sacrificing lower ranked lower ranked entities. And I wanted to have a look at these slopes, which is why I zoom in. This is until generation 150, and this is generation until generation 150 from the old notebook. So let's see. Again, the peak around 1000. The plateau around 1000. The plateau here, we know where that is. 1362. And the slopes, well, they're definitely higher, but what I want to know is where the elbow is, and I could say that it's around somewhere here. So it's well, maybe here, and let's just say here, about here, and that's about generation 30, whereas the elbow in this case is around here. Generation 20. The elbow, as in where the slope actually, changes, so drastically that it's noticeable. But anyway, yeah, that's the difference. So you could say that all this part is due to mutation plus procreation, and starting from here is where procreation starts doing more of the job. Same here. But because the impact that procreation was having on the evolution was so minimal in the old evolution scheme, compared to the new evolution scheme, the slopes are different. And because somehow the slopes are different, the entire plot is different, because everything is raised by about 300. So that's about it for today's session. But I still want to keep stressing the point that because the conditions and the problem space will change, in many unexpected ways, it's not always a good idea to have the entities at the lower end, where this is high, this is low, to have all these entities just struck out because new ones had to be there, and they had to go away to make space, to make room. I don't think that's wise. I need a way to, compromise. It's not exactly a compromise, but balance it out. And I'm sure that if I used some other procreate function, such as the oligopoly procreate, which so far has proven to be very robust and performs better than favoring highs. Oligopoly performs a lot better, not a lot better, but somewhat better than Monopoly or Procreate, or just Monopoly Elite Procreate, or the Lonely Procreate. But one problem solved. I thought I would have to find the right mixture of procreate functions in order to get rid of these peaks and dips. It turns out all I needed was a new evolution scheme. But maybe I could work with these different procreate functions in order to achieve that balance that I just talked about. And maybe next up, no. One of the next things I'll do is try changing the problem space. Is that the right phrase? Is that the right jargon? The right term? I don't know. But try changing the conditions, that's what I mean. So that they're not static, so that they're somewhat dynamic. Okay, that's about it. See you in the next one. Bye.